Okay. Hello everyone. Today the last day of summer school and last lecture will be given by Jesse. And thank you for your great lectures. And you can start now.
Thanks again for having me and for showing up to these lectures as well. Yeah, it's been a pleasure. So this is lecture 4 of the 4-lecture series on minimal submanifolds and spheres. In this lecture, we will make good on our promise to compute the Morse index and nullity of some homogeneous minimal hypersurfaces in round spheres. We're going to focus on one in particular, and we'll see that that computation is sufficiently involved. This lecture is very technical. This is the most technical of the 4 lectures by far. As such, I've made 2 decisions to compensate. One is that this lecture will be shorter because otherwise the amount of material would just be overwhelming. And second, I think it might be worth reviewing for the first 10 minutes or so what was discussed last lecture, just to make sure that we're all on the same page. So that will be the first part of this talk, just a rapid review of what it is we talked about and where it is we're going. Then in the second part, we will discuss the main technical tools that we need to calculate the Morse index of homogeneous minimal hypersurfaces in spheres. So as I mentioned last time, the process I'm going to describe is a 4-step process. And each of those 4 steps has a tool or formula that's needed for you to be able to carry out that step. So I'll describe those 4 technical tools, but first we're going to need just a couple slides on compact Lie groups and representation theory. I can't review all of representation theory here, but 1 or 2 slides maybe would be good. And then finally, in the last part of the talk, we'll give the application. We will compute the Laplace spectrum of the SO5 invariant minimal hypersurface in the 9 sphere. And by virtue of having the Laplace spectrum, by which I mean both the eigenvalues and their multiplicities, we will deduce that the Morse index is 275 and that the nullity is 35. So let's recall what it is we're doing. We are considering hypersurfaces in round spheres. Recall that a hypersurface is homogeneous if it's the orbit of an action of a Lie subgroup of SON plus 1. And it's called isoparametric if all of its principal curvature functions are constant. Okay, in general, we're going to use G to denote the number of distinct principal curvatures, because in general, the principal curvature functions need not be distinct. Okay, a priori, G is any integer between 1 and n minus 1. Okay, so every homogeneous hypersurface is isoparametric, and every isoparametric hypersurface is either minimal or CMC, where by CMC I mean constant mean curvature, where the constant is not 0. Okay, so we discussed last time the striking results of Munzner. Munzner showed that if you have an isoparametric hypersurface in a sphere, then there are only certain options for G, the number of distinct principal curvatures. They can be 1, 2, 3, 4, or 6. And we talked about how there's a very big difference between the cases of G equals 1, 2, and 3 on the one hand, and the cases of G equals 4 and 6 on the other. G equals 4 seems to be the richest case by far, at least as far as we can tell. Munzner also showed that the cone on sigma is a real algebraic variety. Okay, so it's the level set of a homogeneous polynomial, and strikingly, the degree of that polynomial is G. Okay, so I'm gonna let capital F denote this polynomial, and this is nowadays called the Cartan-Munzner polynomial. We'll see some explicit examples. We saw some examples last time, and we'll see another example later in this lecture. Okay, and we talked about how if little f denotes the restriction of the polynomial to the n sphere, then the range of little f is the closed interval -1, 1, and the endpoints are the only critical values. Moreover, all of the level sets with height in the open interval -1, 1 are isoparametric hypersurfaces with the same number G of distinct principal curvatures. So you get this sort of parallel family of CMC and minimal hypersurfaces, which is quite beautiful. And the multiplicities of the principal curvatures alternate m plus m minus, m plus m minus, and only one of these, exactly one of these, is minimal. Okay, it's the one corresponding to c equals 0. We discussed also how for c equals plus or minus 1, the level sets are minimal submanifolds called focal varieties, and their codimensions are equal to m plus minus plus 1. And there's this geometric interpretation of this function little f. It's cosine of g times the distance to the focal variety v plus. So we have this partition or decomposition of the round n sphere into minimal and CMC submanifolds. Okay, so the problem at hand is this. We have our homogeneous, so we're restricting to the homogeneous setting now. So we have our homogeneous minimal hypersurface, sigma, compact, I should say, and oriented. G is the number of distinct principal curvatures of sigma, and delta sigma denotes the Laplacian of sigma. And my convention is that the Laplacian is negative definite. In this case, the Jacobi operator of sigma simplifies. It's just a shift of the Laplacian. Okay, it's just negative of the Laplacian plus g times the dimension of sigma. Of course, the dimension of sigma is just n minus 1. So the notation I'm going to use is that J sigma has eigenvalues denoted by the letter mu. Okay, so there's some negative eigenvalues, then there's the 0 eigenvalue, and then there's infinitely many positive ones that go off to infinity. The multiplicities are finite. Okay, I'm using little l to denote those multiplicities. And the problem at hand is to compute the Morse index, which is the sum of the multiplicities corresponding to the negative Jacobi eigenvalues, and the nullity, which is the multiplicity corresponding to the 0 eigenvalue. Okay, so to do this, we need the spectrum of the Laplacian that's equivalent, because the Jacobi operator in this case is just a shift of the Laplacian. Okay, so this has been done already when G is 1, 2, or 3. So the challenge for all of us is to do this when G is 4 or 6. It's an open question to do this for any of those with G equals 6. It's the G equals 6 case is extremely daunting. We did try, actually. We did actually attempt the G equals 6 case, and the calculations got pretty bad pretty quickly. So we will settle for the G equals 4 case, and we will settle on the two that we know. So the two that we know are, there's this 8-dimensional example, SO5 mod T2. We're going to prove that the Morse index is 275 and that the nullity is 35. And then pretty much the same method, we won't go into the details, but the same method also gives you that the index of this example for k equals 3 is 39, and the nullity is 11. Okay, so how are we going to do this? So again, we need the spectrum of the Laplacian, by which we mean the eigenvalues and their multiplicities. So really, kind of, although I've stated the result like this, index and nullity, there's sort of a more detailed statement, right? There's a stronger statement that implies this. Okay, for the 4-dimensional hypersurface, right, what we obtain is this list of Jacobian eigenvalues and their multiplicities. Right, if you add up those numbers in blue, you get the index. And for the 8-dimensional minimal hypersurface, again, what we get are these eigenvalues here and the multiplicities on the right. And you add up the blue numbers and you get 275. The purple number is 35. Okay, so how did we do this? That's the question. So what we did was we took Bruce Solomon's method, who considered the case of G equals 3. And we took his method and we refined it. We made it a bit more algorithmic, a bit more of a sort of a, an algorithmic method, and we extended it slightly. We added sort of a part 4 to the method, whereas Solomon had just 3 parts. We needed necessarily to add a part 4 because we were unable, for good reason, to we were unable to get a formula for the eigenvalues, right? We just had this algorithm. Okay, so what is this 4-step process? So sigma is homogeneous, so you can express it as G mod H, right? And there's a G invariant Riemannian metric on it. So the first step is to decompose the L2 functions into G invariant pieces. Okay, these G invariant pieces are called isotypical summands. I'll indicate how to do this a little later. Okay, so this is like a Fourier decomposition. then what you want to do is, I mean, the idea essentially is to somehow diagonalize the Laplacian, right? You want to compute the Laplacian on each piece. So you want to take the Laplacian and you look at it on W1. And because of G invariance, the Laplacian preserves W1. So the Laplacian on W1 sends it to W1, the Laplacian sends W2 to W2, etc. And so you want, to represent the Laplacian on W1 as a matrix, you want to represent the Laplacian on W2 as a matrix, and so on and so forth. But to do that, you need a basis. But if you actually just take some, random basis of W1 or W2, it's going to be just a nightmare. You don't want to take a basis for the whole WJ. Really, fortunately, you just need a basis of a very small subspace of WJ. Okay, so we're going to call this a generating basis. I'll be more explicit later. But this generating basis, B sub j, is not a basis of WJ. It's a basis of a very small subspace. Okay, and the point is that by G invariance, this is enough. Okay, and the key point is that B sub j is a finite set of functions, and it has this property that you see there. Wj is the span, not of the etas alone, but of eta circle G. So what you then do is for each of the functions in B sub j, you calculate the Laplacian. Okay, and calculating the Laplacian is not so hard. The problem is you have to express the result in a useful form. So you have to calculate the Laplacian and express the result in terms of the basis functions B sub j. That is actually quite non-trivial. That's actually one of the harder things in this process, which is, a bit strange, but true. But if you're able to do this, you then get, you can then express the Laplacian on Wj as a matrix, a finite dimensional matrix, square matrix. And the eigenvalues of that matrix are, of course, those are the eigenvalues of the Laplacian on that piece. Okay, so for Solomon, this was enough. This actually resulted in a formula for the Laplace eigenvalues, and he was able to stop there. Okay, but for us, the eigenvalues are more complicated. We get irrational eigenvalues, some of which are not expressible in radicals. We're not going to get a formula. And so we're concerned that this process will just go on forever, right? We're concerned that we just have to do this for all of the WJs, right? And we only have finite time. So we need some way of ruling out all but finitely many of the WJs. And this is the extension. We need an upper bound on the eigenvalues in WJ. So the point is that to compute the index, we don't actually need all the eigenvalues. We only need those in this interval, right? We only need those in this interval. So we only really care about the WJs which have eigenvalues in this interval. So all of those that don't satisfy this, we can just sort of ignore. But then the question is, which are those? So what we're going to do is we're going to state an eigenvalue bound. And the point is that all the eigenvalues on Wj satisfy this inequality here. Okay, whatever this means, I'll explain what this means. And the point is that if this right-hand side is less than or equal to negative g times n minus 1, then the Wj is irrelevant to us and we can ignore it. And so the result is that we'll end up with a finite list of Wjs and therefore a finite list of finite dimensional matrices. Okay, so this is the plan. Okay, but to execute all this, we need quite a bit of input. So first of all, let's review very briefly a few aspects of Lie groups and representation theory, just very quickly. So let's let G be a compact connected Lie group. A maximal torus of G is a subgroup of G that's isomorphic to a torus and is not properly contained in any other torus subgroup of G. Okay, so these exist. And moreover, any two maximal tori in G are conjugate, so you don't have to really worry about picking the wrong one. Somehow any one that you pick is fine. And moreover, every element of G is contained in some maximal torus, right? This is a basic theorem about compact Lie groups. This is so fundamental that we have a name called the rank. And the rank of a compact connected Lie group G is the dimension of the maximal torus of G. So here are some examples. Okay, these are familiar. The rank of SO2n is n, so on. The rank of G2 is 2, of course. That's why it's called G2. The 2 is there because it's the rank. And if you haven't seen this before, the way you're supposed to think about this, or at least the way that I think about this, is that the rank is essentially a measure of the complexity of your Lie group. It's somehow almost a better measure of the complexity than the dimension. Intuitively speaking, rank 2 is pretty friendly and rank 3 is fine. But once you're in rank 4 and higher, it sort of becomes really calculationally intense. As much as possible, it would be nice to stick to rank 2 and 3, because then the calculations are significantly more manageable. Things get very, very nasty in high rank, and you have to work very hard. We're going to need a little bit of representation theory. So let's let G be a compact connected Lie group of rank R. Let capital T be its maximal torus. The maximal torus is a Lie group, so it has a Lie algebra. The Lie algebra will be denoted little t, right? And little t you can think of as RR. Okay, so how can you understand a complex G representation or a complex G module? Okay, and for me, that always means a finite dimensional vector space. Okay, how can you understand it? The way to do this is to think about how the maximal torus acts on V. But actually, you don't really think about how the maximal torus acts on V. You think about how the Lie algebra little t acts on V. So you think about how the Lie algebra little t acts on V. And the idea is to look at, for this little t action on V, you look at the simultaneous eigenvectors and simultaneous eigenvalues. Okay, and those have funny names. They're called weight vectors and weights. So a weight vector is a non-zero vector, little v in V, that is essentially a simultaneous eigenvector of the little t action on V. And then the simultaneous eigenvalue, now it's not a number, it's a linear functional on little t, right? So the point is that x, which is, oh, that's a typo. X should be in little t, not little t star. Sorry about that. So for all x and little t, the point is its action on V, it acts by a scalar multiple, but that scalar multiple depends on x. Okay. So on t, here I do mean t star, there's a useful partial ordering that's too technical to explain. And the point is that you can say that alpha 1 is greater than alpha 2, but you don't use the word greater, you use the word higher. And the theorem, the sort of the fundamental theorem of representation theory of compact connected Lie groups is the theorem of the highest weight. And this says a bunch of things. The first thing it says is that every complex irreducible G representation has a highest weight. Okay, so there's some weight that is highest relative to this partial ordering that I refuse to explain. Moreover, we'll need to know that up to scale, there's actually a unique weight vector, a little v, with weight alpha. That will be important to us later, actually very crucial. Moreover, there's a bijection between the complex irreducible G representations up to isomorphism and the set of dominant integral elements of G. Okay, I won't explain what that is either. What you need to know is that the dominant integral elements of G, whatever they form a subset of a certain lattice in T star. So little t star, you're thinking of it as RR. Inside that is a lattice, which you can think of as Z to the R. And inside Z to the R, there's some subset, sort of like almost an upper half space or something. And this parametrizes the complex irreducible G representations. Okay, so you can sort of visualize this, for example, if the rank R is 2, right, you get some subset of a two-dimensional lattice, right? And therefore, if the rank is 2, then the complex irreducible G representations are parametrized by a pair of integers. And that's what's going to happen for us, because we're going to be dealing with rank 2 exclusively. If it were rank 3, then they would be parameterized by 3 integers. Okay, I'm going to use this notation V sub alpha is going to denote the complex irreducible G representation up to isomorphism corresponding to alpha. So it's the one whose highest weight is alpha. Okay. Right. So now on to the technical tools. So like I said, there's 4 steps and each step requires a tool. So step number 1, we're going to need Frobenius reciprocity. We're going to need a Fourier decomposition of the functions on sigma. So sigma is a homogeneous space, right? And here sigma doesn't have to be a minimal hypersurface, by the way. It's just, this is just some arbitrary homogeneous space with a, I guess I should say with a G invariant metric. Capital G is compact and connected always, and H is a closed subgroup. So the first thing to notice is that the space of L2 functions in this context is not just a vector space. There's actually a G action on it, right? Elements of capital G act on L2 functions in the way that you see there. And so given this extra structure, given the fact that the L2 functions have this G action, what you'd like to do is have some sort of Fourier decomposition of the L2 functions that respects the G action. Okay, so this is given by a theorem called Frobenius reciprocity, or Peter-Weyl theorem. And it says that there's an isomorphism of G modules like so. Okay, so the space of L2 functions from sigma to C is isomorphic abstractly to this direct sum of copies of V alpha, where alpha ranges over all possible representations of G. So more accurately, over all the possible dominant analytically integral elements. Okay, and moreover, the multiplicity, so the number of times that V alpha occurs, is given by this. It's the complex dimension of this set of vectors V and V alpha such that that's true. So each of these pieces is called an isotypical summand. And these are the pieces on which we're going to study the Laplacian. We're going to restrict the Laplacian to each of these pieces. Okay, and we're going to want to know, obviously, the dimension of these pieces. It's a basic thing to want to know. And so clearly, that's the dimension of V alpha times M of alpha. Okay, now the dimension of V alpha is actually often straightforward in practice, right? This is sort of a representation theory exercise. You can use Weyl's dimension formula, for instance, to calculate it. However, M of alpha, even though it's seemingly given by this friendly formula here, M of alpha is actually, that can be quite non-trivial to compute. And this is somehow the first major stumbling block of this method. You have to be able to compute this number in a useful way. So you have to either find this somewhere in the representation theory literature, or you ask your representation theory friend, or you have to do something here. This is actually, it's unfortunate, but this M of alpha is actually not so easy to compute. We were lucky in our case. I mean, to be quite honest, we were quite lucky. Okay. So we want to compute the Laplacian on each of these isotypical summands, but we have a problem. And the problem is that these are very abstract, right? I mean, just we have this abstract isomorphism, but that's not good enough. We're differential geometers. We need to do explicit calculations. And to do explicit calculations, we need a basis. And we don't just want a random basis, we want a good basis in which the calculations are reasonable and maybe respect the symmetry and these sorts of things. So what would that mean? Okay, this brings us to the linchpin of this entire method. This is the concept that makes the entire process work. This is the concept of a highest weight function. This is the engine that drives this entire process. Okay. Suppose you have a G equivariant function, vector valued function on sigma, and it's valued in some irreducible representation V sub alpha, and I'm going to call it H. Associated to this G equivariant function H, we can build an associated C valued function called the highest weight function of weight alpha. And I'm generally going to use Greek letters to denote these things. And what you do is you take H, which goes to this, vector space. This could be like R20 or something. And then you compose H with the projection onto a particular complex line. And then you identify that complex line with C. Okay, obviously that depends on the identification you pick, but that ends up being immaterial. Okay, so this complex line is the line that I mentioned earlier. The point is that in V sub alpha, there's a unique vector up to scale having weight alpha, right? That was mentioned a couple slides ago. Okay, so it does depend on this choice of V, but that ends up not mattering. The important thing is that it depends on H. Okay, so if you have a large supply of these equivariant functions, then you get a large supply of highest weight functions. And that's ultimately what you need. Okay, so what does this do for you? It turns out that these highest weight functions have a lot of really wonderful properties for our purposes. So let's let HW sub alpha denote the set of highest weight functions of weight alpha. And that's not just a set, that's actually a complex vector space. Right? You can add two highest weight functions and get another one. You can scale by a complex number and get another one. So this is a vector space, so it has a basis. And I'm going to let B sub alpha denote a basis of this vector space. Okay, the first fact is that the dimension of the space of highest weight functions is exactly M alpha. That's the multiplicity from earlier. And the second thing that's great is that if you look at the span, so if you fix a highest weight function, let's say eta of weight alpha, and then you look at all the functions you get by taking linear combinations of eta circle G, where G ranges over all elements in big G, then that G module is isomorphic to V alpha. So if you put those two together, what you find is you actually get a very concrete sort of description of these isotypical summands. Okay, so the isotypical summand V alpha direct sum with itself M alpha times, you can think of it as the span of eta circle G, where eta ranges over this basis of the highest weight functions, and little g belongs to big G. So the upshot is that we can understand this isotypical summand provided we can get our hands on a basis B sub alpha of the highest weight functions. So that is that's sort of the crux of step 2, is to get an actual basis of the highest weight functions of weight alpha. This is, in my opinion, the most geometric part of the method. This is where you really need to use the geometry of your homogeneous space in a serious way. And this is where we use the embedding. Okay, this just repeats what I just said. So it turns out that these highest weight functions have even more properties that are great. They satisfy some really nice algebraic and sort of differential geometric properties. So we mentioned that it's a vector space, but the set of highest weight functions is a vector space, but more than that is true. It turns out that you can multiply two highest weight functions and get a new highest weight function. And the weight is exactly what you think it is. It's alpha plus beta. So if eta has highest weight alpha and zeta has highest weight beta, then you can take powers, you can take monomials and get another highest weight function. And moreover, the Laplacian, this is the Laplacian on sigma, respects highest weight function, preserves highest weight functions. So the Laplacian of eta is still highest weight, and its highest weight is alpha, and its weight is alpha. And moreover, you can take the dot product of the gradients and get another highest weight function of weight alpha plus beta. This is a very good thing. In particular, this is useful when applying the Laplacian product rule, because the Laplacian product rule involves Laplacians and dot products of the gradients. And we will need this in a very crucial way in applying the method. Okay, one last tool. This is the bound that was referenced earlier. This is our sort of contribution or an extension to this method. So let sigma be a homogeneous space. Again, doesn't have to be a hypersurface. Okay, it's just an abstract Riemannian homogeneous space, I should say. And let little g and little h be two capital G invariant metrics on sigma. And let's say W is a finite dimensional subspace invariant under both Laplacians. So what we want is a bound on the G Laplace eigenvalues on an isotypical summand W. Okay, how will we do that? The strategy is to compare the G Laplace eigenvalues with the H Laplace eigenvalues, where H is some simpler metric that we like better. Okay, so maybe the metric G, little g that we're working with is just some horrible metric, but maybe the homogeneous space also admits a normal metric, right? That would be little h, and so then we can play the eigenvalues off of each other. The punchline is this eigenvalue comparison lemma. Every G Laplace eigenvalue on W satisfies this upper bound. Okay, R min is the minimum eigenvalue of the dual metrics. That's the metric on one forms with respect to H inverse, or the metric on, again, the metric on one forms, and nu max W is the maximum eigenvalue of delta H on W. And the point is that if you pick H nicely, then this right-hand side is something that you can actually compute. And in practice, we will actually be able to compute this right-hand side, and that gives us a usable upper bound. So the reason I'm explaining this is that this lemma will identify those finitely many isotypical summands that we actually have to worry about. Okay, that's what this is going to do for us. Okay, that was all background. Let's see how this works in practice. Let's actually run this method to calculate the Laplace spectrum and therefore the index of the 8-dimensional minimal hypersurface in the 9-sphere. Okay, let's first say what that hypersurface is. There's a very nice concrete interpretation of it. We're going to think of sigma as the set of skew symmetric 5x5 matrices of length 1, norm 1, that have eigenvalues 0, plus or minus I cosine pi over 8, plus or minus I sine pi over 8. Okay, that set, that's a set of skew symmetric 5x5 matrices. It turns out that that is an 8-dimensional minimal hypersurface in the 9-sphere, where we're thinking of the 9-sphere inside R10, and R10 is identified with little SO5. Okay, and this is a homogeneous minimal hypersurface because the Lie group capital SO5 acts transitively upon it, and the stabilizer is T2. So this is exactly what we're looking for. We're looking at. Just for interest, it turns out that the Cartan-Munzener polynomial has this very nice geometric description. And in general, the Cartan-Munzener polynomials often have very sort of clean, elegant geometric descriptions. But of course, if you were to write this out in coordinates, you'd get a mess. Writing these things out in coordinates is sort of horrifying. But okay, so what you do is you think of R10 now not as little SO5, but you think of it as lambda 2 R5. You think of the elements of R10 as two forms on R5, and you can do this procedure where you take x wedge x, norm squared minus norm of x to the 4, and that ends up being the Cartan-Munzener polynomial. It's a quartic, has the correct degree, right, 4, and sigma is the level set intersected with the 9-sphere, it turns out. I have to emphasize, because this has been many times when I give this talk, I'm asked about the metric on sigma. And the striking thing about this metric is that really there's no repeated sort of numbers when you write it in terms of the isotropy representation, right? I mean, all these 4 numbers are different. So what that tells you in a sense is that, this metric is not Einstein, right? This metric is really sort of, as far as we can tell, sort of the only thing that recommends it is that it's the metric you get from a homogeneous minimal hypersurface in the sphere. Like if you were to just look at this metric otherwise, you wouldn't maybe see anything notable about it. It's just some homogeneous metric. So what am I talking about? The isotropy representation, right? That's a T2 representation on the 8-dimensional tangent space. That T2 representation splits into 4 irreducible pieces. And so we're working at a point, that point being the identity coset. And at that point on this tangent space, you can write the metric as a linear combination like so, where little h is the killing form on little SO5, and these constants are the ones you see here. Okay, So that's the hypersurface we care about. Let's run this method. So first of all, our group G has rank 2. SO5 has rank 2. And therefore, the irreducible complex SO5 representations are parameterized by 2 non-negative integers, K and L. And so maybe this looks a little strange because before we said it was V sub alpha and alpha belonged to little t star. The point is that little t star is R2. And what we've done is we've chosen a basis of R2 in such a way that V10 is this representation. So yeah, so we're identifying little t2 or little t star with R2, and we've chosen a basis. Okay, so for example, so here are some examples of some irreducible complex SO5 representations that we'll need or that'll show up a lot. So V10 is the standard representation. V02 is the adjoint representation. And V20 is the representation on the traceless quadratic forms, or yeah, traceless symmetric matrices. The dimension of Vk comma 2L is given by Weil's dimension formula. And Frobenius reciprocity, which we mentioned earlier, gives us this Fourier decomposition of sorts. Okay, this is what you get with this sort of infinite sum. And we need to compute the multiplicities. It turns out that the multiplicities of the k comma odds are 0, which is great. So they don't appear in this sum. That's useful. And the multiplicities of k comma even are given by this expression you see there. Okay, so that's good. So this means that we now know the dimension of each of these pieces, which is very helpful. Right. So the goal is to compute the Laplacian on each one of these pieces. And by compute, I mean we want a matrix representation of the Laplacian on each piece. But to write down the matrix of a linear transformation, as we teach our linear algebra students, you need a basis. So we need a basis of each of these isotypical summands. So remember what we're going to do for each SO5 equivariant function, H on sigma valued in VKL, there's an associated highest weight function of weight KL denoted by eta. Okay, so once you have H, you pretty much automatically get eta, right? So the problem is to find H. What we need to do is we need to find a large supply of SO5 equivariant functions. There's no real method for doing that. This is where the geometry of sigma comes into play in order to find a large supply of SO5 equivariant functions. And the reason we're doing this, just to be very clear, is that each of these isotypical summands that we care about is has this concrete realization as the span of eta circle G, where eta lives in a basis of the highest weight functions of weight KL, and G is in SO5. So our goal is to find a basis, B sub KL, of the highest weight functions. And in order to find this basis, well, it's a basis of highest weight functions, so we need lots of equivariant functions. That's somehow the point. So here are some equivariant functions that we found. So one of them is the complexified position function, that's x. One of them is the complexified normal vector, that's n, right? So those really come from the geometry of the embedding. Okay, this is valued in V02, and this is valued in also in V02. You can take their wedge product, that's valued in V12. And also you can take certain polynomials of x and n. We're going to take these polynomials, q and s of x. Q is this one, and s is this one. Right, so this took us, not obvious to find those. This is where the geometry came into play. Now for each of these equivariant functions, there's a corresponding highest weight function, and I'm using Greek letters for that. So psi, nu, rho, kappa, and sigma are the corresponding highest weight functions. Okay, So the first proposition, again, this is very non-trivial. This takes a fair bit of work. We needed some, induction arguments for this. This set here that you see, the set of monomials, psi to the A, kappa to the B, nu to the C, rho to the D, sigma to the E, satisfying these conditions, A, B, C, D, E are non-negative integers. This is a basis of the highest weight functions of weight k, comma 2L. Okay. So I mean, somehow you need to find enough equivariant functions that you get a spanning set, but you can't have too many because then it's not linearly independent, right? You need just the right number of equivariant functions to make this work. In a sense. Okay, so this is not trivial. Like this takes this takes a fair bit of work to actually prove this, right? So you have to prove that this is linearly independent and spans. But okay, so you prove this, great. So now we're on to step 3. And in step 3, we have to, first I have to move my Zoom thing. We have to calculate the matrix representation of the Laplacian on each isotypical summand. Okay, the first step in doing that is to calculate the Laplacians of each of these functions. So the Laplacian of psi, Laplacian of kappa, etc. And you need the dot product of the gradients. And like I said before, the main point here is that you need to express each result in terms of the original functions. You need to express the Laplacians and the dot products of the gradients in terms of these powers of psi, kappa, nu, rho, and sigma. This is not trivial at all. And this is where you need to both use somehow the properties of highest weight functions to make, in a sense, an educated guess. By the properties of highest weight functions, for example, that the Laplacian of psi will be another highest weight function. So it's a linear combination of basis highest weight functions. But then the question is, what is that linear combination? And that's where you need to use sort of the differential geometry of the hypersurface. Okay, but once you've done this, what do you get? If you can compute these Laplacians in a nice way and the dot product of these gradients, then you can use the product rule for the Laplacian to compute the Laplacian of any of these, right? That's the point. And what that accomplishes is that now finally we have calculated the Laplacian of f for each basis function f, and we've expressed the result in terms of these basis functions. And that's exactly what it means to have the matrix of a linear operator. Okay, so that's what it means to have the matrix of the Laplacian on this isotypical summand. So we have succeeded in our goal. Okay, but the problem is we don't want to do this for all infinitely many isotypical summands. We need to rule out all but finitely many. So let's see how this works. So in this case, the Jacobi operator of sigma is just negative Laplacian minus 32. So we, therefore, in calculating the index and the nullity, we only need to consider those isotypical summands that house Laplace eigenvalues in the interval negative 32 to 0. So the question is, which isotypical summands have this property? If you go back to the eigenvalue comparison lemma and you sort of plug in all the data, you need to have a reference metric H, and for that we'll use the normal metrics. There's a normal homogeneous metric on SO5 mod T2. That'll be our reference metric H. And that's a much nicer metric. Then you can fill in the right-hand side of this eigenvalue comparison lemma, and here's what you get. You learn that every Laplace eigenvalue on this isotypical summand is at most this number. So therefore, we only need to consider those isotypical summands for which this right-hand side is greater than or equal to negative 32, because those that are less than negative 32, have the property that lambda is outside that interval. Okay, but there are only finitely many pairs k comma l that satisfy this, so that reduces everything finally to a finite computation, and this is what you get. These are the k comma 2l's that end up being relevant. You have the matrices of the Laplacian. For some reason, we use only in this step, I think we use the negative of the Laplacian. I'm not sure why we did that. Yeah, and so you have these matrices from these, from the calculations done earlier, and the eigenvalues of those matrices are the eigenvalues you're looking for. And the multiplicities are given in this nice way by the dimension of v comma 2l, which is you have by Weil's dimension formula. And so there you go. That's the result. That's how you do this. So this is the method for SO5 mod D2. You can also run this method for the 4-dimensional hypersurface in S5 that we looked at, SO3 cross SO2 mod Z2. There are maybe a couple of minor differences, but for the most part, it's more or less the same. So to conclude, I just want to wrap up with this one last question. So for each of the homogeneous minimal hypersurfaces, well, we either know the nullity or we don't. And for the ones for which we know the nullity turns out, just coincidentally, to always equal the dimension of SON plus 1 minus the dimension of G. That happens every time. And what that means geometrically is that all of the Jacobi fields are rotational. Right? So they're generated by the SON plus 1 action. So that's kind of interesting. And there's a nice consequence of this from the point of view of geometric measure theory. A result of Allard and Almgren says that whenever you have the property that every Jacobi field on sigma that's a hypersurface in Sn is rotational, then the desingularizations of the cone are all normal graphs over the cone. That's used, for example, in a very famous study of Simon and Solomon, who study the desingularizations of the cone over the Clifford hypersurfaces. Right, so there's this famous paper of Simon and Solomon that they look at the Clifford hypersurfaces in the sphere, they look at the cone over those, and they look at the desingularizations, and this is a crucial fact that they end up using in their study. Anyway, so the question poses itself: if sigma is a homogeneous minimal hypersurface, or more generally isoparametric, I guess you could ask. Yeah, you could still ask that for isoparametric. Is it the case that every Jacobi field is rotational? I don't know. Sort of an interesting thing to wonder about. So I'll leave it at that. Thank you very much for your attention, and thanks again for inviting me here.
So thank you. Is there any question or comments? I think there is no question or comments. So thank you so much for your great lectures.